Thank you. Good morning, everybody. As he said, this is the Go Speed Tracer talk. I'm Richard Johnson with Cisco Talos, and I am the research manager of a small team that does vulnerability research, primarily doing tool development, vulnerability discovery, using fuzzers, writing crash triage tools. We do a little bit of work on mitigations. We have Free Sentry, which is a use after free mitigation. We have recent MBR blocker code that's all open source on GitHub. That'll prevent things like full disk encryption based ransomware, things like that we saw with Petya recently. And then we do some other reverse engineering type stuff. So the agenda for today's talk is essentially to briefly discuss a few different applications for tracing that you may come across in your day-to-day jobs, whether that be for program recovery, or things like understanding code coverage or corpus distillation, and then talk a little bit about the work that's been done in guided fuzzing up till now. This talk isn't about a new fuzzer or anything like that. This is about understanding how tracing engines can be used in guided fuzzers and how to optimize the design and the performance of the tracing engines. So we'll talk about binary translation, which is one method for essentially instrumenting binaries on the fly as you execute them, and allows you to augment the functionality so that you can record a trace, and also the mechanisms that are built into your CPUs, like the Intel BTS, branch trace store, or the new features like Intel processor trace. And then I've got some demos and a whole suite of tracers based upon all the technologies that you'll hear. We'll go through each one of them and do quick live demos and show you how they operate and how they compare as far as performance goes. And then at the end, I have a live demo of the new Intel PT processor features inside of AFL and HongFuzz for Linux. So essentially the goals are to understand the attributes of the tracing and what makes a tracer better for different applications and how to increase the performance of that. And then just generally understand the architecture of, if you're going to write one of these tracing engines, what's involved, and if not, then how to possibly integrate the tracing engines I've written into your own software. So for tracing, we can use it in software engineering practices. We might be a little more interested in the security applications for malware analysis. Depending on the tracing engine you decide to use, they have different attributes for anti-debugging and detection from the malware layer. But they're used all the time for things like behavioral analysis in sandboxes or in unpacking malware, things like that. The Microsoft had a mitigation bounty that was collected from a tool called K-Bouncer, and that uses a tracing engine based upon last branch record, and I'll briefly touch on that. And then other things that build shadow stacks or do data flow analysis also need a high-performance tracing engine. In my day-to-day job, we mostly are looking for bugs, so we apply tracing to corpus distillation so that we can find the minimal set of inputs that we want to target for tracing a particular network protocol or file parser. We use it for guided fuzzing, which allows us to use the techniques that have been developed in mutational fuzzing and iteratively work towards a more refined state and determine which inputs we should continue fuzzing so that we're not wasting our time overlapping or continuing to mutate files that don't get us to any interesting code paths. And then finally, in crash analysis, I've released tools a couple of years ago that focused on things like when you get a crash and you observe that it's a read access violation, how can we use tracing to actually track the memory as it executes through the program and determine whether or not there's constraints on that would truly make it only a read AV, or if you manipulate the input, whether or not you can reach something like execution control or heap corruption or something like those. And so those tools are out there already. Those are on our GitHub at github/talos-vulndev. The MoFlow tools in particular are some of the things that I've done in the past for that. And then also now GDB has hooks that are available that expose some of the underlying tracing engines that I'm going to discuss that allow you to essentially, if your stack is corrupted completely and you don't know where you came from, you can actually ask it to dump the hardware buffers, and the hardware will actually have the last few branches that you executed. So for doing recovery of bad crash states, it can also be useful. So how do you start working with tracing engines? Basically, there's APIs that we're all pretty familiar with, probably your ptrace on the Unix POSIX side, debug engine, and even signals can be used as a debugger-based feedback mechanism. In the Linux kernel, they have a pretty robust and developed tracing infrastructure, currently now named the Linux Tracing Toolkit. That's all built in and includes everything from K-probes to access to these hardware tracing mechanisms. And on the Windows side, we have things like Nirvana and App Verifier and the shim engine. These things are not well known by most people. I would say the best reference source for that kind of thing for using these hooking engines is Alex Ionescu's talk last year at Recon. And it's a great talk. It's esoteric hooking or something along those lines, and it goes through how the Nirvana system works so you can capture system-wide interrupts and system calls basically with a single pointer control. So really cool stuff. App Verifier actually is really cool. I was using it because it exports a layer that allows you to essentially just define data structures for the hook points that you need. And it's fully supported by the system, and you know it's not going away, so you don't have to fight with whether or not your engine's overriding or using some esoteric functionality, or creating the process, then stopping it, and then injecting a library or something like that. You can just go ahead and use a supported API. And then the stuff that's closer to what the topic of interest today would be the Linux perf subsystem that typically has been used to expose counters like cache misses and number of seconds for a particular instruction to execute and things like that for profiling. But they've now extended it to include wrappers for things like the Intel PT infrastructure as well. And then on the Windows side, there's an API called Windows PDH, and it's so poorly documented I couldn't even find the definition for what PDH is supposed to stand for. It's a performance monitoring toolkit. When you go into the process monitor or something like that and you see statistics about the process executing, that's where that's coming from. There isn't really any current support in Windows natively for doing granular program tracing like block coverage or anything like that. So typically if you're developing software and you want to collect coverage, the traditional tools would be things like gcub and lcub that the compiler will instrument every one of your functions, and this is typically applied to function level coverage as opposed to block level logic coverage that will allow you to track which decisions were made inside your program. So you get an idea of reachability and the paths and the execution over time, but you don't have the ability to determine, did we fully cover all the decisions that were made in here. It can do a mapping to line-based coverage, so you can see which lines were executed, but it's not as well exported or exposed to things that are appropriate for fuzzing or finding vulnerabilities in an automated fashion. And then the granddaddy of the binary translation that a lot of academic research has been done on is Valgrind, or Valgrind. You have cool tools like Memcache D on that, and there's a taint checker that's built into that as well. It's always been a good platform to develop ideas on, but it's not cross-platform and it's really slow. It has a robust but not a very performant engine. So basically we need to look at something that's cross-platform and more performant to pull off what we're trying to do. And your typical tools of choice there are Dynamo Rio and Pin. And then we've also developed tools and open sourced them based upon Dynast, which is another academic toolkit that works primarily on Linux, but it has some hope for working on Windows soon, and it allows you to do static binary rewriting. So we'll get into the attributes of each of these and a little bit more. There's new ones coming on the block like Frida and some others that incorporate the JavaScript V8 just-in-time compile engine. But they're also not targeting low-level granularity, and I don't think they're as performant as the other options. So on the hardware side, you probably interacted at least with this first one, single steps and breakpoints. And you may have heard about the Intel branch trace flag, which will convert single steps over to basic block steps. So instead of doing a single step, it will actually fire an interrupt every time you do a branch instead. And then the LBR, last branch record, that's the one that I mentioned was used for mitigations. And it's highly performant. It uses its own set of registers, but it doesn't allow you to record much of a trace. And Branch trace store was the next mechanism that was designed to be able to capture all block traces into a ring buffer or interrupt mode programming. But it's not very fast either. It's actually slower than any of the software DBI approaches. And we'll show you demos of that. But the latest hotness ever since last year or so, Intel's included something called Intel Processor Trace. And that's like the exciting new stuff because it's actually designed with performance in mind. And it's kind of the highlight for where I'm trying to take the tracing technologies. And just to mention, I'm not doing any work currently on the ARM core site functionality, but it's also similar to the branch trace store where you can do branch tracing natively in the core. So we'll switch context a little bit and talk about, what is evolutionary testing or guided fuzzing, where's it come from, that sort of thing. Originally, evolutionary testing was really appropriated in government research, people that were doing white box testing of hardened and critical systems. So, aircraft operating systems or other things that you would use, setcomp or, reduced compilers that are verified, and they need to ensure that they're doing the highest grade of testing possible. And so the main thing there is that some of the techniques that they adopted or created aren't immediately usable against binary targets because they went from a sense of collecting attributes about the software, like probable vulnerable locations. Maybe an integer overflow detector or something would say that, if we can reach this area of code, then with user-controlled input, it's likely that this is a vulnerability. And so then they would use evolutionary testing to get from point A to point B. You can apply this in binaries, it's just more difficult. So there isn't really a good framework for direct application of those tools. And of course, none of them were ever made open source or anything like that and discussed as far as the internal designs. But they were applied and effectively used for preventing denial of service and that sort of thing in critical systems. In the framework of doing vulnerability analysis for what we do, essentially the idea is to, cheaply, without a lot of user interaction, without having to write protocol definitions or do a lot of upfront work to just, refine the methods that we've been doing for the last 10 years in dumb fuzzing. So this pretty much allows us to apply evolutionary algorithms, which are based around the core principles of the way that genetics work, in the sense that the strongest population, when introduced to another similarly strong population, will mutate and create generations past that have attributes from both. And ideally, those attributes that you see, this input over here gains a lot of code coverage and incorporates this functionality. And if we merge that or keep manipulating that, we'll get deeper and further into the parsers. And so essentially, that's all that the evolutionary algorithms really do for fuzzing, or applied to any approach really, is to continually allow you to iterate through dumb brute force methods and continue to just get the right population just through iterative testing. So it's basically just a really cheap way to find security bugs. And the most popular fuzzer out there right now, can I actually get a raise of hands if you do fuzzing and you've used American Fuzzy Lop? Let me get a raise of hands. Okay, so maybe 10, 15% of you guys. So American Fuzzy Lop is an extremely successful fuzzer. I'll highlight some of the attributes in a minute. But if you've used American Fuzzy Lop, then you're already using evolutionary testing, and you'll know that it's much more successful than using a typical off-the-shelf dumb fuzzer. So it has its merits. The first public talk really that introduced these ideas was Sherry Sparks and Embleton's Black Hat 2006 talk called Sidewinder. Really cool. They were doing, this came out of some of their academic research, but I think they were also targeted at the government sector. I mean, if you look at their slides, they've got ICBM missiles or something, in their slide deck and everything. But it had some really cool attributes to their approach. They were the first ones to publicly discuss using genetic algorithms in a fuzzing context, so that's kind of their win. They never open sourced and became public, but their slide deck's really good. They use a context-free grammar to describe the inputs, and then they manipulated the grammar itself. So rather than take a byte stream of your network or file format, it would actually define a context-free grammar that relates fields and has delimiters and things along those lines. That structure that describes the input would then be manipulated and used as a model for generating further inputs. And so you saw stuff like this also out of the OULU group and Protos, their work. And the main problem with that, of course, is you have the upfront cost of developing the model to start with. They didn't get to the point of model refinement that was automatic, where you could have a loose model saying, I know this is gzip data, and I know this is some sort of TLV set of fields. But they did, which would eventually allow you to kind of refine that down. But they did introduce the idea of using a grammar and fuzzing the grammar as opposed to fuzzing the bytes themselves, which is interesting. They had a pretty slow tracing engine. That's a major drawback of their system. But they did have a pretty cool process or evaluation for fitness, which is the other key part of the genetic testing, genetic algorithms. And they used a Markov process, which, so this is a demonstration of their grammar kind of here on the right, where each one of those represents, if you start with A, then you wrap it in what S is in, and so on. So you build a string out of a set of numbers, and the bottom left is 1, 0, 2, 4, 7. Essentially, you walk through those steps on your series of input, and then you output at the bottom X, A, B, B, A, D, X. So that's their mutator algorithm. And then their evaluation algorithm is this Markov process, which essentially allows you to evolve weighted whether or not you'll go down certain paths or whether or not you are more likely to keep an input that went down certain paths is based upon an over time evaluation of all inputs seen. And so cheaply creating a log of where all these inputs have been is actually not an easy thing to design. I would say this was a good model, and then it took about 10 years until we ran into American Fuzzy Lop to get this next best model. In between, everybody seems to want to write out these really verbose logs of all blocks hidden, and then post-process that, and then kind of try to merge those results together, rather than keep a continuous flow of things that self-weight and create a model iteratively, just like you're creating your inputs iteratively. But yeah, so basically it was never open source, which is too bad. It had some great concepts, and people kind of forgot about them, because the next year, we had Jarrett DeMott talking about his evolutionary fuzzing system. And at the time, the PyMA framework was really pretty popular. It was able to do code coverage using some of these tracing mechanisms. But it was still pretty slow. It used the debugger API, or it used the branch trace flag. But Jared took a very, very academic approach. This was for his PhD thesis. And essentially, he ended up trying to get closer to what scientists do when they're tracking actual biological evolution, which includes a lot more variables and environmental analysis, and essentially just made it overly complex. By making all these variables and not having a good data management layer, he just threw it into a SQL database, which had to be queried on every iteration. And so we've gone from a point where you might get one iteration every few seconds or every 30 seconds to getting thousands of iterations a second just through increasing the performance and applying this. So generally speaking, the value that Jared brought was just a little more awareness. He made it open source. He did it in a toolkit other people were using and familiar with. But due to more or less not great engineering practices, it just never panned out as something beyond an idea. And then that brings us to today, all the way from 2007 to 2013. Michael Zaleski released the American Fuzzy Lop, and this is truly a revolution in the next generation of doing testing. He started with these ideas, and Tavis Ormady also was starting with these ideas back in 2007. Michael Zaleski wrote a compiler plugin, and at the time, I didn't actually pay a lot of attention because I have always been interested in third-party black box testing. At the time, I was working at Microsoft, so I had internal source code, but we couldn't use anything that was open source. So anything I wanted to evaluate that wasn't our own code was black box binary stuff. So I didn't really look into the first iteration, Bunny the Fuzzer, but it had a lot of the similar ideas as American Fuzzy Lop. So it was out there and just never caught on anywhere. Tavis Ormady and Will Drury took a different approach. They were writing Flare at the time. Flare was built on Valgrind as a tracing engine, and it was basically allowed you to tear apart the outer layers of a program where there might be checksums or compression, and get right into the deep internals of the program and start fuzzing at that layer. And of course, these guys at some point all ended up merging together under the Google security banner. And now I think these ideas are free flowing internally and things like that. But American Fuzzy Lop essentially is a compile time instrumentation. It was out of the box anyways. But it's simplified the approach to the genetic algorithm, specifically in keeping track of your entire execution time. So if you're fuzzing something for weeks on end, it keeps a memory mapped byte array that essentially what it does is it takes a source block and a destination block of the the branch. It XORs them together and creates a bit of a hash that fits into like 64K hash table. And essentially indexes into that hash are keeping the number of times that edge has been traversed. And the number of times that increases, that'll increase if you go into loops, or that will increase anytime it's observed to execute that particular edge. And over time, you can determine whether or not a new input is interesting compared to the entire set of observed inputs over time. So that way you can keep drilling down. And he does this through shared memory map, which we've taken the trouble to port over to Cygwin so that we can use this as the basis for our Windows fuzzing as well. But using the memory map between the child process that's being fuzzed and the observer process, of course, is a pretty fast mechanism. It's actually engineered to be idiot-proof and to be very fast and to work out of the box. And it took the compiler approach, which is much more performant in general. So you don't have to use a translation engine. And at the end of the day, it's actually found a lot of good bugs. Up here on the right, it even has a GUI, which is pretty rare in the fuzzing instance. But it's cool because, in particular, this GUI allows you to track over time and see, on the far right there, it kind of gives you some stats on how many paths have you seen. It evaluates when new paths are discovered, which inputs are generating the most new paths, and then keeps a corpus. And the cool thing about the corpus is it can be reused in other fuzzing techniques as well. So for example, every input that it keeps around and adds to its population or pool of inputs that it might fuzz, each one of those exercises a different functionality in the program. And so if you go and target something that is closed source and doesn't have the ability to be instrumented through American Fuzzy Lop, or is too slow when instrumented, like Microsoft Word or any of the major application suites that do productivity, then you can actually take a known good set of different and minimized inputs and use more traditional fuzzing systems like Redamza or ZZUF or any of the other ones, which is pretty cool. And it brought a fork server into the mix as well, which is just a much more efficient way of spawning processes. When you're on Linux, you get a copy on write, duplication of the address space, so just pretty much instantaneously can spin up a new process to test. And it has a couple other cool things in there. Persistent mode fuzzing, which allows you to directly instrument some functions and say, this is the function that I want to start fuzzing at. And then at the end of that, you write a little function does memory cleanup for you, and then it will loop back and start again. So I'm working on something similar to that in the Windows space by generating threads. So you identify where the thread create occurred that then later on reads the input that you're interested in. And then you basically allow that thread to go through its process, which usually is reading in data, putting it into structures, and passing it back to application to do something with it at a higher level. You can just respawn threads there. So we can escape the forking model and just go with the native threading model instead. Those that might have seen my talk last year, we did some work to bring Windows native forking using undocumented APIs in the Windows kernel. And it turns out to be a real pain in the ass. At the end of the day, if you use Windows system calls to write your own version of a fork, the Windows higher level like subsystems like CSRSS are not really aware of this new process that you generated. So it works okay for wrapping libraries directly if you're writing your own wrappers, but it doesn't work for if you want to run a bunch of iterations of Adobe Reader really fast. But yeah, back to American Fuzzy Lop. The main observations here, keep it simple, stupid, definitely does still apply. Doesn't matter how technical your application of a technology is, actually producing a tool that is easy to use right out of the box, has configuration options and warnings when you're not using it correctly. Like AFL, for example, will analyze your set of inputs that you start with right off the bat, and it will execute through each one, and it'll tell you, I think you have too big of inputs here. You don't need a 3 megabyte sample of a PDF to do PDF fuzzing, and in fact, the bigger the number of bytes that you have, the less likely that a single bit flip is going to cause a substantial change to the program. So minimizing your input set down to the smallest trigger possible to execute that type of code is the way to increase efficiency in your search space, essentially. But yeah, performance is a top priority, which I find to be heavily lacking in almost every security tool out there. And in my talk last year, I specifically focused on cost reduction and the importance of performance in security testing and automated testing. At the end of the day, if I can do a 50% optimization for performance, then I have to buy half as many cores as I would have otherwise to compete with the other guys out there that are doing fuzzing at scale. So we are in a phase of doing security testing automatically that performances matters, because you got guys like the Googles and the Amazons and the others out there that are in a position to scale infinitely. So optimizing and reducing your cost set to be able to compete in that market is important. Then the last, oh no, there's a couple more. Okay, so then there's HongFuzz. It's another fuzzer from Robert Swicky out of Google. It wasn't very interesting until 2015. It basically was pretty much a dumb fuzzer. It was easy to use, but wasn't a lot going on with it. But in 2015, he started adding guided fuzzing features and specifically going after wrapping the Linux perf interface. So the tracing engines we're about to discuss, he basically has interfaces for all of them right now out of the box. Unfortunately, he did add Intel processor trace support, and I was unable to get it to work. And I'll talk and mention why a little bit later. But it is pretty cool. It does block coverage now, and initially it also was kind of weak. It only kept one input rather than a whole corpus. He didn't have a good algorithm for tracking the performance of a single input over time. Kind of only the strong survive. In the case of it's only the elite survive in genetic testing. But it's cool. It's cross-platform, and it actually now also has source-based instrumentation. And if you're writing your own fuzzers or trying to optimize or tweak something specifically to a certain target, HongFuzz is a lot easier to hack on than AFL is. Because AFL has the curses interface, and it's interleaved. It's one like 10,000 line C source file. It's kind of a pain in the ass to actually hack on and do anything with. HongFuzz is a much more approachable code base. But now it has all the main features that you pretty much need to do corpus tracking over time. It uses a Bloom filter to determine whether or not it's likely that you already generated this, things like that. And then ArgP and those guys out in Greece just recently, a couple months ago, released something called Coronzone. Or I'm not sure if it's public or not yet. He sent us a copy to review. It's pretty cool. It adds in pretty much all the features that were good about AFL and HongFuzz, but he's also trying to bring back in some data type awareness, in the sense that he's isolated inputs into kind of different buckets, things that are chunked formats like MP4 or video files, or things that might be container formats like Word documents that were using structured storage, or XML-based compressed files that are actually a series of inputs below that. So essentially, he allows you to create a higher level container data definition and then tear it apart and then do all the good fuzzing underneath. And some additional stuff with some of the type modeling. You can get as deep into that as you want. You write your own custom serializer function that knows how to take it apart, and then from there, he manipulates the model internally. So it's one step towards being more specific about your data, which makes it more efficient in the long run. A lot of formats, if they have compression or checksums or something like that, you need to write special hooks to fix that up anyways. This all integrates it into the system. But the only real problem with it is it's using a really, really slow tracing engine again. So that's kind of where I found opportunity to work on this area and give away these tracers so people can speed up their cool ideas. A couple other honorable mentions. We won't talk about them at all in detail, just simply Joxin Koretz, Matalaz is out there also working in the same space. He kind of took the duct tape approach, where off-the-shelf tracers, off-the-shelf mutators. Let's just throw some Python glue in there together, and hey, I've got a tool. You're not going to end up with a well-engineered system that way, and that's pretty much my evaluation. It's cool. He wrote a web interface as well for it to kind of manage it. I think that's the value add there. Something like what Grindr already was putting out there. But I did actually look at the Fuzzing Run Tracer Code plugin, which was the pin tool that they use, and that also was written back before anybody really took a look at how to do things performantly. And then CovFuzz, if you are a fan of doing Node.js-based stuff, is a similar reimplementation of a coverage-driven fuzzer using ASAN code coverage feedback. And so it's just easy to set up and also very, very hackable. So after all of that, what do we get out of that? What are the properties that are interesting and things that we want to survive in the next evolution of fuzzer creation? Well, obviously we need a fast tracing engine. If you're doing code coverage driven fuzzing, then we need to be trying to get the fastest code coverage engine possible that's accurate, and we need to come up with algorithms to track it over time, right? So the logging functionality has often been overlooked as a really key point in doing efficient tracing. And Intel themselves has recognized this, and that's one of the reasons that the new CPU-supported Intel PT is so awesome, is they actually created a very, very lightweight base logging mechanism, which makes it way, way faster. And then also on top of that, we don't want to get overly complicated with the evolutionary algorithms. What we're using now, the lightweight stuff, works, so why change it? Let's not pollute the simplicity of design. And if we can get portable systems that are easy to use with extra helper tools like some of these come with, that's cool. If not, you can always just borrow them from those code bases and reuse them. My recommendation is if you're going to be writing your own system from scratch or want to use something that's a good basis to develop on top of, HongFuzz was probably my highly recommended approach. If you just want to go fuzz something today, use AFL. Hands down, it found shell shock. It found so many bugs after the fact, but like there's hundreds of bugs attributed to AFL. Hanno Bach is pretty much writing his whole fuzzing system around AFL, it seems, but it's shaking out bugs everywhere. It's really good. It's free bugs, essentially. All right, so binary translation. This is a whole other section. Essentially, the idea is that you have a JIT engine for your native instruction set architecture, right? So you have x86 to x86 JIT, and it knows how to disassemble and do data flow analysis, all the internal compiler types of logic that you would expect, but it's targeting binaries, and it's allowing you to interleave your own instructions into the cached and optimized version of the binary. So the general idea is real simple. You hook the execution of a program through a custom loader that replaces the ld.so on Linux or on Windows, and essentially it performs all the runtime linking and loading of your dependency libraries. And instead of executing immediately, it loads each individual function into a code cache, or depending on what mode you run it in. But generally speaking, what they do is they find the entry point, start executing at every branch. If it's a new block, they then bring it into a code cache. They make a copy of it, and at that point in time, they allow you to modify the code in its cache. From then on, every execution of that basic block will be from the code cache, and it keeps a read-only memory mapping of the original binary for any static data references or things like that. So you don't have any stability problems or any issues with the traditional x86, is it data, is it code in your disassembly, because at runtime it's able to discover where the new code is, and it keeps the copy of anything that needs to be there for the future. So very robust, it works very well, it works on, depending on the engine of your choice, it works on ARM, it works on x86, it works, a lot of these were developed back in commercial Unix days, so it works, some of these engines go back to working on Spark and HPUX and things like that. But generally, what we care about is that it allows you to do highly granular instrumentation. Previous work that we did, we actually did all the way down to instruction level instrumentation to track data flow. In this particular case, we only need to do block-based instrumentation. So one just side note here is there's a lot of cool work still going on in these software DBI engines. VMware in particular is continually doing more work there. they bought Dynamo Rio via the purchase of Determina, actually. Determina was a company that did in-memory anti-exploit technology, essentially using the Dynamo Rio engine. The guys that were at MIT Lincoln Labs wrote Dynamo Rio. It was an extension on top of a HP platform. And they brought it to x86 architecture and essentially developed it to the point where it was capable of being the base infrastructure for a commercial product. And then later on, VMware bought them and ended up open sourcing Dynamo Rio in the long run as a BSD license, which is pretty awesome. So anyways, as we talk about these different DBI engines, usually the question comes up, why is one 10 times faster than another if they're performing essentially the same thing? And all of that has to do with how they perform, how they link the basic blocks together in memory. They create these traces that are hot flows of code, because these are designed to do optimization at their core, but at a higher level optimization typically. It's typically like groups of functions that need to be optimized and accessed more frequently as opposed to block level stuff or instruction level. But yeah, the main advantage is it works everywhere. Essentially, if you get the right kit, it can be faster and is faster than most of the hardware tracing engines that were available up until 2 years ago. And it's easier in a way, since you can also do your hooking engine directly in the DBI engine, you don't need to use other frameworks for doing your hooking. So it's easier to do things like turning on and off your trace based upon the code that you observe executing and things like that. So more dynamic things that you can still do with other engines, but it takes more work. The main disadvantage is, by design, this introduces a new context switch into your software architecture. So normally context switches occur when you execute system calls, and what has to happen is the CPU needs to store all flags and registers to memory and then go ahead and switch over into kernel context. Well, this adds a layer because the broker, the translation engine itself, is another context layer. So it has its own execution state over here. That's the one that's loading code into its cache. And your program has its execution state that's actually executing the cache. Because of that, you get a new context switch, and context switches are expensive due to non-code locality, right? So when your CPU loads memory into its L3 or L2 buffers, essentially those are of a limited size. So if you start executing code somewhere else completely different in memory, it invalidates all the cached memory translation, and so that's where a lot of the overhead comes from. The only other thing is that each one of these also has to have their own disassemblers built in. So unlike a hardware-based engine where it's natively in the die of the CPU, in this case, you're relying a lot on their ability to decode the same instructions. So this isn't such a big deal in compiler-oriented things. It can be if you use the ICC compiler and turn on all their heavy optimizations, and that omits code that maybe Dynamo Rio or Pin hasn't been updated with. You're pretty safe with Pin because that is developed by Intel. It uses the Z decompiler, so if you need software-based and as close to instruction support as possible, then you would use that. Dynamo Rio supports just about everything you can imagine, but there's academic work on doing compatibility testing across disassemblers, and it's in general shown that not all of them have 100% compatibility. So you may or may not have instruction support for certain features of the ISA, and if you're up against some malicious code that's aware of that, they can use that to do detection or possibly break out of your monitored process. But it's generally a really great tool to use, especially for doing things like security testing against clean software that's not an actively defensive nature, right? So I'm not going to bother saying much about Valgrind. I already said what I wanted to. It's just out there. It's obligatory. It's accessible, but I kind of wish people would stop writing stuff on top of it because it's non-portable, and all that work needs to be re-implemented. And also, Dynamo Rio has a Dr. Memory tool, which is essentially like the ASAN crash analyzer or Bang exploitable in a way. One of Valgrind's best features is that if you run a program crash through it, it will give you a nice dump and tell you, this memory buffer was corrupted and all sorts of things like that. So That was one of the only reasons to use Valgrind up until recently, but now Dr. Memory's cross-platform, and it runs twice as fast and does all the same stuff, so I would recommend moving away from Valgrind. Let me get another raise of hands. Who has done any work with the DBI, has played with pin tools, anything like that? Okay, cool. All right, so a fair number of people. If you get into doing dynamic binary instrumentation, pin is typically the first toolkit that you'll come across because it's getting some widespread adoption. It's easy to use. It has high-level APIs that are really, fairly straightforward. I have an example here in a second, but it takes like 10 lines of code to get up and running and doing block tracing. Problem is that based upon their design, you're not able to do things like, if you only want to hit trace, you only want to observe whether or not a block was executed. You don't care about how many times or where it came from, just that you hit that code. You can't do that in pin because they don't give you your hook until after that's already been built into a trace. So they've loaded the code, they've analyzed the code, they've put it into these paths that they know will get executed in sequence, and then they let you look at it. The problem with that is that their optimizations happen before yours do, and so they're not aware of any changes that you might make to the code, and they can't optimize it. So pin ends up being quite a bit slower. And also because they've done the optimization early, and they don't give you like an intermediate language that is direct access to the opcodes, you're more or less limited to injecting trampolines at arbitrary locations. So that can be useful, but once again, code locality reasons, oftentimes you'll be jumping somewhere completely different in memory, and so you incur a large overhead. In fact, so here's an example of how simple it is to get into. So this trace function is just a callback. You register a callback at the beginning of your library, and you say, I want to see every time you've created a trace. Traces are generated whenever a back edge or an indirect branch is taken. Okay, and so you get to enter the trace, then you walk the basic blocks on the trace, and for each basic block, in this case, we're inserting a call back to an analysis function. That analysis function can do whatever you want. Typically it would be something to log the basic block execution. And let me pull up a little demo here. I can just show you interactively what kind of performance we're talking about. Right, so get to play the game where I don't get to see what I'm typing. Let me zoom in here first. All right. So as you can see, I have several engines here based upon Dynamo Rio, Branch Trace Store, Intel Processor Trace, Dynans. How are we doing on time? Okay. All right, so and pin and all that. So we'll do pin real quick. Basically what this demo does is it iterates through about 100 arbitrary PNG files using the PNG test program that comes with the library. And all I'm trying to demonstrate here is a visual example of the performance. Obviously, I started off with the slowest one first. Pin, while it can do tracing, and this is all doing code coverage-based stuff, it'll take roughly a minute or so to fully execute this. And once again, the main reasons for that are the engine design that generates traces based upon black edges and using some of the older literature and their approach to that. And also because it's later on in the optimization phase that you get to do your instrumentation. I'm not even going to bother letting it finish, I guess, because I'm really short on time. So just so that you guys can see that, and then we'll talk about Dynamo Rio and flip back, and you'll see the difference between Dynamo Rio and pin. So basically, I call Dynamo Rio the connoisseur's dynamic binary translation. The reasons are numerous, but primarily it's because you get to actually go down and synthesize instructions directly into the program at arbitrary locations. So instead of that one function that was like 5 lines to put your hook in there, you got to do a little bit more work, but you can get down to the point where you're literally adding in arbitrary assembly instructions anywhere you want. You can do liveness analysis on your flags and registers to make sure that you're not trampling on anything else. I mean, it's as deep as you want to get into the weeds and basically do runtime assembly injection, DynamoRio is the way to go. All I would say beyond what I've already said is essentially it's also portable. It's actively developed all the time. It's in GitHub. It's BSD licensed. You can ship it yourself. Pin is a commercial license. You can't ship it with your code. It's closed source. It has a lot of reasons it's not great to use. Other than the only thing Pin has going for it is high-level API. DynamoRio has all the other good stuff. It also has, in the Docker memory, they're trying to isolate this out, and this is really promising for the future. They have a shadow memory system, which is very important for doing data flow tracking. And so if you want to build advanced tools, advanced crash analyzers, all that framework is already there. It's really tightly integrated into the Docker memory toolkit right now, so you'd want to go modify that. But they're working to bring that outside and make it more of a library. You can build standalone tools as well. The usage model for DynamoRio has all kinds of different ways of operating. There's just a lot to say. A whole talk on security-focused tools for DynamoRio is probably in the future for me because it's just really cool. But to give you an example, it is quite a bit more complicated. I left the instruction or the comments on this one, so it's not as dense. But basically, as you can see here, when the basic block is first seen from the program, you're able to instrument it before it's stored in the cache. And so you can get down to the point of actually modifying each individual instruction. It has multiple phases, similar to a compiler. So depending on the phase of optimization that you want to hook in, you get different levels of instrumentation ability. And it's not all that complicated, but as you can see here, I'm having to save the arithmetic flags because I'm going to inject the increment instruction, which will manipulate the flags if you get an overflow. And then, it actually, each individual operand you have to convert and tell it how to generate and things like that. But if you're willing to go through the work, you can get as deep in injectable code as you want. And there's about a 20% execution runtime overhead for DynamoRio without any instrumentation. But if you write your tools well and actually go through the effort, very little overhead is incurred on top of that base 20%. So you can write very efficient tools, and I'll give you an example of that. And just visually, you can see that this plugin's doing the exact same thing, and it's just skimming through it. The other one was going to take over a minute, and this should, I believe, have the output of time at the bottom here. At the end of the day, that takes 11 seconds, so this is a 6 to 8 times speed increase just right off the top without doing a lot of extra work. That's using the function that I just showed you. So using the right engine, doing a little extra work up front, and you're saving yourself, hundreds or thousands of hours in the future of your fuzzing executing and getting more money, more bang for your buck out of your hardware. And then, I'm sorry, I'm hoping I don't go over on time. I've got a few more things to cover. Dynast is a really huge, developed over time across 2 universities and using the government kind of platform, which is never a good sign. The cool thing about Dynast is actually that Barton Miller, the guy that coined the term fuzzing back in '91, and the whole story about electricity through the dial-up line causing input to be modified on his terminal, then do Unix crashes or whatever the hell. That guy is a professor at University of Wisconsin, and he runs basically a security and binary team over there. And he and the University of Maryland, I think, are the other guys working on the engine together. It's super fast. It's awesome. If you can use it, use it. It right now works really well on Ubuntu 14, and if you get the compile situation figured out just right, you have to self-compile certain things and use the OS-provided libraries for certain things, and if you don't get the right recipe, you're fucked. But Dynast, when it does work, it's as fast as it's going to get. It statically rewrites to disk, so all of the problems with code locality go out the window. There is no separate cache. There's no separate code context switch incurred. So we have a tool that we released last year already for AFL called AFL Dynast, and it allows you to basically modify commercial libraries, off-the-shelf stuff, enterprise-grade software, instrument them using this, and use AFL, all the good engineering in that engine, to fuzz test like software that matters. So it's a great tool. Use it if you can. I have a Docker image or Docker config file up on our GitHub as well as part of the AFL Dynast. If you want to skip all the headache of figuring out how to get it run yourself, just use that, or copy the instructions out, run it on your local host, whatever. The other thing I will say is, so we really, 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 really badly want this to work on Windows. So bad that we went in and we wrote support for PE relocations and sent them patches over a year ago, and had some good conversations, but they are slow as hell to, like, no effort trying to get this to run on Windows. It's like when you know that there's this thing here that just needs just a little bit of work, and it's such a complicated system that reverse engineering it and trying to fix all the gotchas that eventually build up over time when you're building a production grade system like this, because there's all kinds of edge case scenarios. But hopefully it can work on Windows in a dynamic mode as opposed to static rewriting, but you lose all the benefits, and it can only do trampoline injection. So use Dynamo Rio if you're going to do dynamic. Yeah, so here's actually our code that we use in the AFL compatible plugin for Dynast. It also has kind of a annoying API. It's a little higher level, but it doesn't get you anything extra. So you got to do work like walk the control flow graph yourself through iterators. It's not a big deal. But yeah, I mean, these are all pretty easy to use, really, for what you get out of it. You can tune binary translation basically by only instrumenting indirect branches, waiting until your input's seen. There's all kinds of ways. Make sure you're only instrumenting the threads that are actually parsing the data. So there's lots of ways to apply this to more heavyweight software in the end. Wish I had 20 more minutes. So basically, I'm going to skip through the old school hardware stuff. It doesn't really matter. If you're going to do hardware tracing, you need to learn how to do program interrupts. That's the lowest level stuff. And let me tell you, if you're doing it on Windows these days, it's a real pain in the ass because of all the patch guard and anti-rootkit technologies. Doing low-level programming on the Linux kernel is still easy and fun. It's a joy. Doing it on Windows is just horrible. But you might be familiar with interrupts already. Obviously, using try-catch at a higher level, but at the lower level, doing single steps, or if you're into demo scene stuff, that's how they wrote to the monitor. There's all kinds of stuff in there. But I want to get to Intel PT. So basically, when you program a CPU and you're doing this low-level programming, there's a whole series of instructions not normally accessible to you in user mode for standard application programming. And these are the model-specific registers, or MSRs. And what they allow you to do is put the CPU into special operating modes, and including some of these tracing functions. It's also how you would do things like set up SMM memory, or enable anything in the PMU, anything that's on core that is not part of your typical operation of the CPU. Those are configured through MSR registers. And they're called model-specific because they change over time, and they add features to the architectures that evolve, and so things like that. And so one of those things is the branch trace store. That was the best tech until Intel PT. And as you can see, this is all actually happens right in the CPU pipeline itself. So in this case, the instructions are being loaded from memory and pushed into the CPU pipeline. In the case of branches, if you flip one flag in these MSR structures over here, you can turn on LBR, BTS, or whatever. And what ends up happening here is that you load hex 1D9 into your EAX register. You load some other registers with some flags and whatnot, or a structure that you point to, and then you simply execute MSR write, which is a privileged instruction, and that will write to that specific register, essentially the configuration that you're looking for. If you do it all right, then essentially you can turn on LBR first. This is actually 64 reserved registers that you normally don't get to touch. They're there. They're as fast as normal register access, so it's pretty much a free tracing mechanism. It can only do 64 branches, though. So at the time of that filling up, normally it would just do a ring buffer. If you have BTS enabled, instead it will fire an interrupt and write that out to RAM. But it's using an older mechanism that's not in the die. Well, it doesn't bypass the MMU, so it's quite slow. So Intel processor trace, this is the good stuff. Essentially, what we're looking at is a new processor feature that lets you do full system tracing for 5 to 15% overhead for recording. This is by far the fastest tracing system that's ever been developed. And it works now. It's been out for about a year and a half. It is supported by Intel System Studio. If you get the right formula, once again, I think it's Windows 8.1 and Skylake, certain models. Linux perf subsystem since 4.1 has also exposed these features. So all you got to do is execute on a command line. I've got it here in a second. To enable a feature, do whatever business you want to do, stop the log, then it'll write it out to disk, and you can post-process it. The tracer itself is kind of like Ring 3 because it has observability over everything happening in SMM, in hypervisors, in your kernel, in user space, the whole range of code protection level or operating level of your CPU. So while it currently doesn't have the ability to stop and interrupt, this is a passive monitor at the moment. It is in the space where it's undetectable by the higher layers. So you could write a hypervisor, for example, that would make it impossible for a kernel to ever be able to detect that this is enabled. So if you're looking at doing tracing applied to malware analysis, that's where the hardware traces are really important because at the end of the day, there's always going to be artifacts at the software layer of translation or hooking that is going to be detectable. In this case, you're at a low enough level that it's outside the MMU, so there's no way to detect cache poisoning or anything else occurring, and you can lock it down because you're at that low level. It's the only mechanism that can be used to do SMM tracing, for example. And then the other big thing they brought to the table, so they bypassed the caches and the MMU, super important, no address translation impact. And then they also created a heavily optimized log format. And this is also, in Broadwell, it wasn't supported in virtualization mode, VMM, but it's now supported in Skylake. So you can essentially do filtering based upon CR3, which holds your the PDE, the pointer to the page tables. And essentially, you can say that I only want to trace things that are operating on this virtual machine, or that's how you can filter it out and figure out which mode to trace in. You can also filter based upon the CPL level, so if you only want to trace kernel space or only want to trace user space, you can do that. The format itself is kind of a bitch. There's taken not, so essentially to reduce the amount of space, they can do about, I think they said like 1 byte per branch in total, and that's on average. They do 1 bit per branch if it's a conditional branch. They do, if it's a indirect branch, and they record the destination address. And then they have other things like, interrupts that are accessible in the log or timing information, things like that. It's a pretty gnarly format, but fortunately there's an open source cross-platform library available from Intel on GitHub, and it's called libipt. Which is pretty crucial. And there's also a standalone kernel library that's separate from the perf subsystem that's a lot easier to understand and read if you want to do your own manipulation of the API. Because it's 90 pages of Intel developer manuals, and if you've looked at those manuals, it's just like page after page of different flags you can set in different operating modes, and if you're in hypervisor, or if you're in this and that, it sucks. So writing your own driver, believe me, is not fun. The general way to use it is essentially to enable it in the CPU. Each core has its own Intel PT operating mode and cache. So you essentially need to be in ring 0 or below in order to enable this stuff because the requirement for MSR programming. You enable it on your CPU itself. All this stuff happens in the compressed log offline. The log itself actually can't really be used intelligently without knowing something about the processing state when it was being recorded, meaning you need the memory maps and you need the original binaries. In order to decode the logs into something useful, it recreates that process space and then parses the log over top of it. For our function and fuzzing and things like that, the reason this is important is it comes into how you do your design of decoding the log. You need to do it before you exit the program, obviously. And also right now, I'm trying to figure out if it's better to take an entire core and pin that to trying to do near real-time decoding versus doing a phased, execute, get the compressed log back, and then decode it. But I have a live demo of that in a second. Here is how you can use it. Like right now off of the perf subsystem, it's really easy to access, and there's a few tools that come with perf that let you do things like, visualize your call graph tree or, gather stats along those lines. And then also the simple PT kernel module, which is what I use, also comes with a standalone tool, just spt command, and execute whatever you want, and then that writes out a sideband file, which is your memory map information necessary to decode it, as well as the log files themselves. And then you can, of course, print it out like this and see your call graphs as well. All right, real quick, let me get a demo of the AFL. This is what I've been working hard on. Excuse the poor typing here. So yeah, I've implemented this in HongFuzz as well as AFL. Just because of time constraints, I'm going to just show you the AFL one because that's kind of the core. Sorry, I'm just trying to get something I can copy and paste so I don't have to do all this typing off. What? So basically, I added a flag to AFL. It's capital P that will do processor tracing. Where's my mouse? Oh, So this is actually, since I'm doing this really quick, this is not using PNG test that we saw earlier. This is using a custom wrapper I wrote for libpng that essentially, I need to run as root because, God damn it, because Intel PT mode requires root privileges, basically. So this is one of those things where AFL is letting me know that if I run without disabling the core pattern here, then Ubuntu will try to snag my crashes from me, and we don't want that to happen, right? Okay, let's try that one last time. Hopefully this will do the trick. And AFL won't yell at me again. Of course it does. Very sorry about this. I should have had this already set up. So what this is doing is telling the CPU scaling to disable. And AFL, of course, wants you to get all your CPU power. Jesus. Am I not root? I am root. Fuck. That's the problem. Maybe. I think that worked. There we go. So what we're about to see is that, so of course, there's some setup bullshit that needs to be fixed. But here's AFL running using the Intel PT hardware-supported tracing engine. And as you can see, we're getting pretty decent performance, 700 executions a second. just to give you an idea, natively this gets about 2,000 executions per second. So overhead is just over 50%. So the next step in conclusions, I know I'm out of time here. Basically, this is all being migrated to Windows as well. Recon in 2 weeks, I should hopefully have a code release for you. All the tracing engines that I've talked about and shown you today are soon to be open source. They're just need to package them up and put them on GitHub. So feel free to contact me offline. Rich in Seattle on Twitter is probably the easiest way. And with that, I would like to just thank you guys. Yes, thank you. Yeah, I'll be around, so you guys can grab me out for Q&A.